And the last one, thermal expansion. For thermal expansion, silicon is 2.33, okay? Steel is 12. Oh, so for this one, you can see the silicon wins win upon the steel a lot, actually. It's around 5 times difference, almost 5 times difference. Thermal expansion, talking about when we heat up the material, how much distortion, how much expansion of the material it will go, okay? So if a larger thermal expansion, that means you will get a lot of deformation when you heat up the material. But the question is, for making some kind of devices like sensors, we don't like the material to expand too much, actually, because most of the material respond to temperature variation a lot, actually, but that will affect your sensor stability. Yeah, so you want to use the sensor in different temperature, right? At a different temperature, but at some elevated temperature, you can have a totally different material property because it's staying too much. So thermal mismatch problem will happen among different materials. So that's not good. So usually you want the thermal expansion maybe in a controllable manner. So silicon you can consider after you heat up the silicon, thermal expansion is quite low. But so for most metal, you can see from steel to aluminum, most metal have a very high thermal expansion property, ranging from like 4.5 is tungsten, up to 25 is aluminum. Okay, give a very high value for most metal material, very high value of a thermal expansion. But for surrounding material from silicon carbide up into silicon maybe semiconductor material, but like silicon oxide is a dielectric material. So most of the surrounding material you can see the thermal expansion is not high. Okay, so the lowest one is quartz. Quartz thermal expansion probably is almost zero, close to zero. So that's why we use quartz as the frequency keeper, the vibrator. Okay, to put inside a watch. Okay, to keep counting the time. Okay, so time will be fixed. Will not change with temperature change. So that's a good thing. For silicon dioxide, actually it's not quartz. Okay, here is still pretty low, 0.55. But for quartz it's almost zero. Okay, yeah. So you can see on the rest of 3 parts of the material property, I think the silicon has a lot of more advantage over steel. Okay, so in this table, steel only win in the first island. In the second island, second column, and break even in the third, but lose in the other 4 to silicon. Okay, so if you can consider to use steel as a good material in the mechanical industry, why not to use silicon to substitute the steel in the future? Actually, it's not a new story. Actually, human has used actually silicon material long ago. Yeah, like before the metallic material, we used a lot of stone, right? So in the Stone Age, actually human used a lot of stones as a mechanical material to cut, to seams, to do a lot of mechanical works. But the question is, even though stone, the fundamental material is considered of silicon and silicon dioxide, those kind of things, although they have a lot of good properties, but they have major problems. Okay, the major problems is that they are very fragile material. They don't yield any plastic deformation. Okay, after a certain kind of strength, they break easily. So they will cause some chipping, cleavage problems. Okay, they are brittle. Yeah, it's a problem compared to steel. So that's why after people invent using metal material to be a mechanical material, we totally forgot about the stone. Until recently, people try to find out maybe stone is not that bad actually. Okay, but the good thing is if we use silicon in a micro scale, okay, the chipping, the cleavage problem maybe a little bit not that bad actually. Okay, because in the small scale, the structures of material will be closer to their single crystalline structure. Even polycrystal material, if you keep shrinking your mechanical structure, the mechanical structure will close to each of the grain. Okay, you understand? So that means it will be closer to the single crystalline material. As you know, single crystalline material will be stronger. It's stronger than the polycrystalline material, because for polycrystalline material, you have a lot of grain boundary. The grain boundary give a lot of defects, and also they will slide to each other, and also they will break along the grain boundary. But if you have only single crystalline material, they will be stronger, much stronger. So even though silicon is brittle material, but when you shrink the size down to the micro size, so the structure will closer to a single crystalline property. So it may be better, maybe okay, maybe lower, so still useful in the micro scale. So that's why we consider silicon as a mechanical material in the micro scale, even nano scale. Okay? Yeah. So this gives us some rough idea and also the comparison among different materials. So you can come back to dig into different materials to see their property in the future. Maybe you will use different material in the future for your work. Okay. Now we have to understand the fundamental properties of silicon. Now we will try to introduce how to do the bulk machining. We come back to our original idea, the goal of this lecture. So actually for bulk machining, the meaning is we want to machine to create some structures on a bulk material. Okay? So you can use different way, etching, using digging, using cutting, using whatever. Mechanical way or chemical way. The purpose is to machine, okay, the whole bulk structure to get the structure you want. Okay, that's the meaning of bulk machining. So there are many different kind of materials you can use as for bulk machining. For example, single crystal silicon, that's the most we used, and you can use silicon like using quartz. Somebody use quartz as a substrate, and you can use gallium arsenide, other different kind of material as well. Because silicon material is most studied in the past 20 years, and also there are a lot of ways to do the machining process. And also silicon material is connected with semiconductor industry. So it's easier to connect the mechanical material with IC or different electricity material devices. So that's why we consider mostly in this class by using the silicon as a mechanical material. We will not mention too much about others. Okay. So for silicon bulk machining, actually they include two different types of bulk machining. The first one we call the isentropic silicon wet etching process. So etching process that means we're using chemical way, okay, to take out the material to form the structure we want. Okay. So isentropic means there's no direction. Okay, all direction are the same. Okay, that means isotropic. So for isentropic silicon etching, with etching, so easily to form the structure if you have punctured holes on the top. So because the etching process going to all different direction has into the same etching rate. So you can see if you puncture a hole on the top, you will form like a hemispherical structure underneath. Okay. If you have like a rectangle hole, so you got like a cylindrical structures, have cylindrical structures underneath. Okay, because they go all direction with the same etching rate. Okay. Okay, so how to perform the silicon isentropic micromachining process? Actually, we will go through a special chemical a special chemical we call the HNA system. HNA means H means the nitric acid. H means hydrofluoric acid. N means nitric acid. It's an aqueous solution, so it's called the HNA system. So the HNA system give you very good, very strong etching process. Okay, so when we look into the detail of the chemical process, we can break into 3 different steps. Okay, so the first step, the purpose of the nitric acid. The nitric acid, when they inside the water, and if we have a nitrous acid involved, it will form nitric acid, and finally give 2 holes to inject into the silicon. So once silicon has 2 holes, it has more ability to be etched, to be oxidized later on. Okay. So the second one will be the oxidation. So the actually nitric acid is a very strong acid to oxidize your substrate. So because you inject 2 holes, and so the silicon accepts these 2 holes and will be oxidized to form silicon dioxide. This is the second step. So after you form the silicon dioxide, also you generate some bubble, hydrogen bubble here. Okay. So after you generate silicon dioxide, the silicon dioxide can be etched away by hydrofluoric acid, HF acid. That's the final step. Okay. So you can consider nitric acid is strong acid, oxidant acid. So you can oxidize the silicon to become silicon dioxide. Then the silicon dioxide can be etched away by hydrofluoric acid. It's 2 steps. Okay. If you consider the first 2 combined into 1 step, so there are 2 important steps. Nitric acid oxidize your silicon into a silicon dioxide, and then the silicon dioxide is etched away by using hydrofluoric acid. Okay, is that clear? Okay, so you combine these 3 steps together, you got the final results of the reactions. So the reactions will be silicon plus nitric acid, hydrofluoric acid. You form the dissolved silicon is kind of special ions, and also your nitrous acid and some bubble inside the solution. That's the final reactions. Okay. So in this system, we have 3 different things combined to each other, including nitric acid, hydrofluoric acid, and also water. Water is not showing here, but we're generate water here. But originally, you can put this agent inside the water. So we can look into the iso H curve. Okay, for the combination of these 3 chemicals. One is we call this hydrofluoric acid on the left-hand side, and the nitric acid is on the right-hand side. So on the bottom, we have the diluent, so for example, like a water or acid, acetic acid. Yeah, acetic acid. Okay, for different things. Okay, so we got this curve. The meaning of this curve is each curve here you see is iso H curve. That means the etching rate is the same on the same curve. So for different curve, they give different etching rates. Okay, for example, you look in the solid line here. So the etching rate for this solid line along this solid line is 940, right? It's 940 micron per minute. It's pretty fast. Consider the silicon substrate is only 550 micron in depth. So if you can etch 940 in minute, in half a minute, you can consume away the whole silicon substrate you are currently using. So it's quite amazing. It's quite high speed. Okay. So usually we don't use that kind of high speed. So as we look into different curves here, so as we go inner this part, the diagram, you can see the etching rate start to reduce. Okay. So from this curve up to this curve, the most bottom curves are around 15.5 micron per minute. Okay. So you see the differences, huge differences. It's around more than around 100 times differences. Okay, the etching rate. Okay, okay. So So we have two systems actually. On the bottom we have either water or acetic acid. Okay. So by using acetic acid as a diluent, you got a solid line here. It's like a buffer, okay, inside solution. So keep the pH level more or less fixed into some kind of value. And the other one by using water. Water is not like a buffer. So when you do the etching, actually the pH level will change during the etching. So the behavior will be different. Okay, so you can see we got two different lines, the dashed line and the solid line. The dashed line corresponding to water as your diluent, and solid line corresponding to acetic acid as your diluent. So when you're using acetic acid as your diluent, it becomes like a buffer. Okay, the buffer can keep your pH level more stable, so you can have a more area of the curve. Okay, for you to perform the etching. Okay. So how to use this table? So now I give you one example. Please take a look at the red line here. So for example, we're using 20%, okay, of the water. It will be here, okay, this line. So we draw one red line along the right-hand side coordinate system. So along this one, in parallel to this one, so we got one line here, and use 20% of the hydrofluoric acid, for example here. So we can extend another line along the bottom coordinate system. And the other side we're using, so we have 20% water, 20% hydrofluoric acid. That means we have left 60% of nitric acid. In total, we have 100%, right? So we have 20% water, 20% hydrofluoric acid. So we left 60% of nitric acid, okay? So nitric acid, you draw a line, okay, along left-hand side coordinate system. So you end out, you will have one intersection point here, okay. So this intersection point will lie onto the second dashed line, right? The second dashed line, roughly, okay. So for the second dashed line, what's the etching rate? So you extend the second dashed line to the bottom to see the value. The value down here is 33. Okay, 33 micron per minute. Okay, so the etching rate for this specific point, for this kind of formula, you arranged, okay, it's 33 micron per minute, the etching rate. Understand? So for each point, you can extend back to the original concentration of different, combination of these three solutions together, okay? Okay, so we look into the water one, so it's a dashed line. But when you look into the acid solution, there will be the fourth line, the last fourth line. It's this one, the solid line, okay? You fall into the solid line. So the etching rate will be different. For acetic acid, you got a higher etching rate, 76.3 micron per minute. It's about twice. Right? Original using water as a diluent, it gives you like 33. But here, if you use acetic acid as a diluent, same concentration, okay, using 20% acetic acid to replace water, you got a higher etching rate, okay, 76. So that means if you keep your pH level more constant, okay, more stable, the etching rate can keep constant, and the etching rate can be higher when you compare to water as a diluent. Using water is not a buffer, so you change the pH level all the time. So the etching rate will reduce and reduce and reduce, so you won't get the final result that high. Okay, there's differences. Okay. Okay, so we mark it down. So that's one important thing. The other important thing is that when you look into the bottom, center, and the top side of the this kind of etching, you will see different results. Okay, from the top portion, if more hydrofluoric acid, if you're using the points on the top portion, for example, in this position, you got a 70%, for example, hydrofluoric acid, and like 15% of your nitric acid, and the rest of 15% of water. So got this point. So this point, even you have a similar, etching rate as the bottom one. So for example, we originally we got this point here. So we extend this one to the top. So along this line, you have the same etching rate, but the etching results will be different. On the top portion, top part, you have more hydrofluoric acid than nitric acid, right? But on the bottom, you have a more nitric acid than hydrofluoric acid. Okay? So if you have a more hydrofluoric acid, that means every time when the silicon to be oxidized into silicon dioxide, the silicon can be taken away quite easily because you have a very high concentration of hydrofluoric acid. So in this case, the surface becomes very, very rough. Because the silicon dioxide is like a protection layer on the surface. If you etch in the silicon dioxide slowly, okay, it's like protection. So the surface becomes smoother. But if you don't have a protection every time, so the roughness will be expand, okay, to become more rough and more rough. Okay, so on the top portion, remember, if you have a more concentration on hydrofluoric acid than nitric acid, you can have a rough surface. But in opposite, on the bottom portion, you have a more nitric acid than the hydrofluoric acid. The surface becomes smoother. Even they share the same etching speed, but the bottom one is smoother because you have a thick silicon dioxide layer all the time for protection, so you won't etch in too fast. Okay. So the extrusion, the very sharp part can be taken away by the hydrofluoric acid easily. Hydrofluoric acid has enough time to take away the sharp points, okay, the rough surface, okay, on the silicon dioxide. Okay, so that's why the bottom one is smoother than the top one. Okay, so that's the important things. So those are important properties I have written here. So high HF, low nitric acid. So it's oxidation limit. We got a rough surface because every time you got a silicon oxide into silicon dioxide, it can be etched away by hydrofluoric acid because you have a high concentration of hydrofluoric acid. So we have in this case, we have a high roughness. But in the opposite, we have a high nitric acid. We have a smooth surface because it's an etching limit. Etching is the HF. Nitric acid is for oxidation. Okay. Okay. So these are two important conclusions we put here. So for your references. So I have mentioned this already. Okay. So maybe we stop here and take a little rest, and we will come back later in 10 minutes. Thank you.